So one of the use of the uh, dual of the circular points denoted by C infinity star is to make use of it to uh, compute the angles between any two lines on a projective plane. But before we look at how to do this in the projective plane, let's refresh our memory on how to compute the angle between two lines. Suppose that I have two lines L and M over here. What I want to do here is that I want to compute this angle theta between these two lines here. And suppose that the line L is given by these three vector homogeneous coordinates L1, L2, and L3, as well as the line of M is given by M1, M2, and M3 respectively. We know that from lecture 1, I have shown that any line that is represented by suppose L and a three vector homogeneous coordinate L1, L2, and L3. We know that the normal vector of this particular line is given by the first 2 and 3 of the line in homogeneous coordinate. Hence, this normal vector here is given by L1 and L2. And similarly, any line of M given by the three vector M1, M2, and M3 in the homogeneous coordinates, we would have a normal vector given by the first two entries, which is M1 and M2 respectively. And in order for us to find the angle between these two lines here, theta, it's equivalent to finding the angle between these two normal vector here in the two vector coordinates that we are now given as the normal vector from the homogeneous coordinates. And we know that this can be found from the dot product of these two vectors. So what we are going to do here, it would be equivalent to L1, L2 transpose multiplied by M1 and M2. And this this would be equals to the magnitude of L1 and L2 transpose multiplied by the magnitude of M1 and M2 transpose multiplied by cosine theta, which is the angle between these two normal vector here. And this is equivalent to the angle between the two lines. As a result, we will be able to compute cosine theta equals to this expression over here. But the problem with this expression is that it's not defined under any projective transformation. What this means is that if I were to transform the lines L and M respectively via any projective transformation, which I denote as H, into L prime and M prime respectively, which is where L prime is given by H of L or inverse transpose, and M prime is given by H of inverse transpose of M respectively, then I wouldn't be able to directly make use of L prime and M prime to incorporate this projective transformation into this equation over here to compute the angle between the two lines after the projective transformation. Hence, this expression cannot be used after an affine or projective transformation of the plane. So we'll make use of the conics C infinity star that we have defined, which is the dual of the circular points that we have defined earlier to do this transformation and compute the Euclidean angles between the two lines after the transformation. We'll just simply put this C infinity star between L transpose and M. This is the dot product. So in this case here, we're no longer just looking at the normal vector of L1 and L2, but we are looking at the whole line homogeneous coordinates here. So this is L transpose here, and we are looking at this guy here, where we incorporate these three entities or three elements into the line vector here. And C infinity star is what we have defined earlier to be this matrix over here, where the off diagonal it's 0 and the diagonals would be 1, 1, and 0. So substituting this guy here, and also M equals to M1 M2 and M3 transpose here into this equation, we'll get exactly what we saw earlier to be L1 M1 plus L2 M2. And similarly, for the denominator terms, we'll get exactly the expressions in the Euclidean space that we have computed in the previous slide. But one of the advantage of doing this by including C infinity star into the formulation is that now we will see that it becomes invariant to projective transformation. And here's the proof, the mathematical proof on why is this so. So recall that I have mentioned that the line transformation is given by H inverse transpose L, where H here is a general projective transformation, and the conics transformation would be, or the dual of the conics transformation is given by H C star H transpose, and we'll transform this into C star prime under any point transformation of x prime equals to H of x. And hence the numerator would transform into this form over here, where we are initially given L transpose C infinity star multiplied by M, and after all these entities, L, C star, as well as M undergoes the transformation of H, we'll get this expression over here, where this guy here, the first term over here, would be equivalent to L prime, and the second term over here, this guy here would be equivalent to C star infinity prime in the transform space, and the last term over here would be the transformation of M into M prime. And we can see very clearly that over here we would have a H inverse multiplied by H, and this guy over here is equivalent to identity. And similarly, we have another term over here which is equivalent to H transpose multiplied by H inverse transpose, and this would also give us identity. Hence, these two terms here can be cancelled out. And now let's look at the result. We will be left with L transpose C infinity star multiplied by M, which is equivalent to what we have begun with. And hence, it can be verified that also that the denominator terms would stay the same, because the denominator term is also the of the same format as the numerator term, and the scales of L and M will cancel out. Hence, we can conclude that by expressing the Euclidean angle into this expression, which incorporates the conics C star infinity, it would be invariant to projective transformation. That means that what happens here is that if I am given two lines here and this angle theta, L and M, and if I were to transform this using any H or any of this projective transformation, then the angle between these two lines computed this way would stay the same. It would be invariant on the projective plane. And L and M are orthogonal if this particular expression over here, L transpose of C infinity star M equals to 0. This can be easily proven from the equation earlier, and here this equation gives the angle between any two lines, L and M, which is denoted by theta here. So if these two lines are perpendicular to each other, then we can pretty much see that cosine 90 degree here is equals to 0. Hence, we can write this expression and use it as a constraint for our observations between any two lines. So once the conic C infinity star, which is the dual of the circular point, is defined or identified on the projective plane, then the projective distortion may be rectified up to a similarity. What this means is that given an image, and if I'm able to identify the projection of C infinity star onto the image, I would be able to remove the projective distortion directly up to a similarity transform. And here's the proof. If the point transformation is given by x prime equals to hx, this is where h here is the general projective transformation, we have C star infinity prime equals to this guy over here, where we call that we can write any form of projective transformation. We can decompose it into these three terms over here. We can factorize it into three terms over here, where HP here is a projective transformation, A is affine transformation, and HS here is our similarity transformation. So substituting these terms into the expression here, we can see that we can group this HS together and call this C infinity star, where we have defined, we have proven earlier that C infinity star, this guy here, it's going to stay the same after it undergoes a similarity transformation. Hence, we'll group this together and call it C infinity star since there's no change to these conics, dual conics here. Then we are left with HP and HA term in this expression, which we can see that these two terms, according to what we have defined earlier, these two terms here, we can express this with respect to C infinity star, which is given by this matrix here, and obtain this particular final matrix here to represent C star prime after the projective transformation. And this is what we will use to denote the C infinity star prime. And it's clear that the image of C star infinity gives the projective V and affine K component, but not the similarity component, because the similarity component here is adsorbed into C infinity star because it remains the same. So there's no way for us to figure out what's the similarity transform after this C infinity star has undergone some form of projective transformation. But we will be able to express this once we observe this guy here, C infinity star prime on the image. Then we'll be able to make use of this information to compute the projective transformation using to find out what's V here, as well as to find out the affine component K from this equation. So recall that the decomposition here is given by these three terms here. So where this is HS, the similarity transform, this is HA, as well as this is HV here. So what we're interested in is to find V and K in our computation here. Now, after having looked at the definition of C infinity star and how it remains invariant under similarity transform, as well as to express it using projective transformation, let's now look at how to do metric rectification using C infinity star. So given the identified C infinity star in an image, that's denoted by C star infinity prime. This guy here is the C infinity star that has undergone some form of projective transformation as what we have defined in the expression in the previous slide. A suitable rectified homography can be found from SVD of this guy over here. So what this means is that suppose that I have my C infinity star. This is the dual of our circular point, and if I'm able to identify this point or this conics on my image over here, then I would be able to decompose this into this term over here using SVD. Since this is a 3 by 3 symmetrical matrix, what this means is that after I have done SVD here, the usual SVD of A, let's say a matrix A, which is n by m, what I'll get from here after the SVD would be U transpose sigma V, or the other way around. I mean, you can put the transpose here, it doesn't matter. But in this case here, what happens here is that U would be n by n dimension, because this is a non-square matrix, and sigma here would be a n by m matrix, a diagonal n by m matrix, which is consisting of all the eigenvalues, and V here would be a matrix of size m by m. So U and V here are both the left and right octagonal matrix of A, and what this means is that they are not going to be the same or the equal size over here because A is a non-square matrix. But if we were to take the SVD of a square matrix C, for example, then the end result would be U sigma U transpose, where U and both of the U's here, they are going to be the same. If this is the square matrix n by n square matrix, then I would have U n by n sigma to be a diagonal of the eigenvalues n by n, and U here would be also n by n. And these two U's are the same actually. And what's interesting here is that sigma would be also its eigenvalue, and it will also reveal the rank of C and A respectively. And here, after we have taken the SVD of the C infinity star prime matrix that we have observed from the image, we can decompose it using SVD into this term since it's a square matrix. And what happens here is that we'll get the eigenvalues, which is 1 and 1, as well as the last term here is 0, because this guy here, as I have mentioned, that sigma here would reveal the rank. So usually sigma is in this case n by n matrix. If I have some values here and then the last few diagonal here are 0, then I would be able to tell all the non-zeros here would be equivalent to the rank of the number of non-zeros would be equivalent to the rank of this matrix C here. So here, recall that C infinity star is a rank deficient conics because it defines 2 points I and J, the circular point using lines. So these are the degenerate conics with rank 2. So the rank of C infinity star prime here is equals to 2. Hence, we can see that after the singular value decomposition, the eigenvalues here in the entries here would only have 2 non-zero components, and the third one will be 0. So we can see that this reveals the rank of C infinity star prime as well. And what's interesting here is that this matrix here will be directly equivalent to C infinity star. And hence we can take the left and right octagonal matrix U here to equate it to H, which is equivalent to this term here that we have seen earlier, because this, after the decomposition, this is equivalent to U and this is equivalent to U transpose here. So now we can equate this and find all the terms of K and V inside here up to a similarity ambiguity, because we cannot find HS here since HS is absorbed into this C infinity star here. Now, let me show you an example on how to do this metric rectification. Previously, when we talk about the line at infinity, we saw how to make use of the line at infinity, the identification of the projection of line at infinity on an image to do projective rectification. But I have also mentioned that after the projective the rectification from this step to this step, well, we cannot, we are still remaining a affine distortion here. So now I will show how to make use of C infinity star, the dual of the circular points, which is a degenerate conics, to do metric rectification of a finely rectified image. This means that this is left with a fine distortion here. So we are going to now identify this guy here and remove this distortion. So after we've seen earlier that after the projective distortion removal, we will turn parallel lines into parallel again. And here, because of the projective distortion, we can see that it parallel line meet at a certain point here, a certain finite point. But after the removal of projective distortion, parallel line becomes parallel, but we are still not able to recover the angle here, where the true angle here is supposed to be 90 degrees, but apparently it doesn't appear so on the image. So now the next step is that we are going to identify C infinity star prime on this image, and then making use of this, we'll be able to compute HA and remove it. Then we can see that after the affine distortion removal, the perpendicular line would become perpendicular again here. Now, we have seen that C infinity star prime is equal to this expression over here, which can be further simplified into this expression here, since HS, the similarity transform, is being absorbed into the conics, into the degenerate conics here, which can be rewritten into this form here, this equation here. So this is simply just putting HP here, bringing HP here into the left side of the equation. So HP becomes H inverse P, as well as H transpose P becomes H inverse transpose P on the left side. And on the right side, we are remaining HA C infinity star and HA transpose here. So now let us collectively write this term here on the left side as C prime prime star infinity, where this C prime prime star infinity denotes the image of the conics after removal of the projective distortion here. So because here we are undoing the projective distortion by bringing this projective transformation onto the left side of the equation here. So what happens here is that C prime prime star infinity would still contain the affinity transformation, but we would have the projective distortion removed here. So now we can compute C prime prime star infinity from the image where we have removed the projective distortion, which we have seen using the line at infinity in the earlier slide. And because this C prime prime star infinity is what we have defined to be an entity, to be the dual of the circular point projection, where the projective transformation has been removed and we are still remaining the affine transformation. Hence, the objective here is to identify C prime prime star infinity on this image, and to make use of this to compute HA such that we can remove the affine distortion from this particular image here. And we can compute this. We'll see that we can compute C prime prime star infinity from two pairs of orthogonal lines from this image here, which is still distorted by affine transformation, but we already have the projective transformation removed from this particular image here. Now suppose that I have the lines L prime and M prime in the affinely rectified image, and this is the image that we are looking at. So we'll be able to identify this orthogonal line pair L and M on this particular image here, since we know that this corresponds to the real world where it's supposed to be perpendicular to each other. And of course, in this image, because it's still subjected to a affine distortion, this means that this guy over here is not going to be equals to 90 degree from this image, but in reality, it's going to be 90 degrees here. So we'll be able to identify this pair of lines L prime and M prime here, which we can directly substitute into this equation here. So L prime M prime, we'll be able to identify this, and we'll let's say denote this by L1 prime, L2 prime, as well as L3 prime, and transpose, and M prime that is equals to M1 prime, M2 prime, and M3 prime here, transpose. I'll be able to substitute this into this equation here, which we have seen earlier, where L prime and M prime are these two lines over here, and C prime prime infinity star is going to be what we are interested in solving here. And since we know HA here, it's given by, this is a affine transformation, is given by this term over here, which consists of the only unknown here is going to be K, where K here is actually a 2 by 2 matrix. This means that there are 4 terms inside here. So what we can do here is that we can substitute this into this term over here, where C infinity star here is what we know to be 1, 1, 0, and the off diagonals to be all 0, and we can substitute this inside this equation here. So now, since L prime and M prime here are known from the image, which we can measure this by, we can easily compute this from any 2 points here to express this line over here in terms of this equation here, these two equations here. It would be simply any 2 points here. The cross product of any 2 points here would give us this two lines over this L prime, as well as any 2 points on M prime here, would give us the cross product of this would give us M prime over here. And we can observe these two from the image. And now substituting everything back into this octagonal equation here, which is equating to 0. This is a constraint here, which because we know that the two lines are perpendicular to each other. And hence, we'll now see that we are only left with the unknowns of K and K transpose here, which we can rewrite this into as 2 by 2 matrix. So there are 4 elements, but only 3 independent elements inside here. So what we can do here is that once we have this equation, we can express it out into this form over here. Since we only need 3 independent numbers or elements from S. So S equals to S11, S12, S21, and S22 over here. And since we know K is a symmetrical matrix here, so this means that S12 must be equals to S21, or K transpose is a symmetrical matrix here. So this means that these two guys here must be the same. Hence, we can rewrite this into this form over here, and we'll get this equation over here, which is in terms of S11, S12, and S22. These are the 3 unknowns over here. 2 constraints here from 2 octagonal pair of line can be stacked together to give us a 2 by 3 matrix. So this guy here is actually it's a 1 by 3 vector transpose, and this S here can be rewritten into S11, S12, and S22 here. So this will give us 1 constraint. This means that 1 pair of octagonal line will give us 1 equation here in terms of the 3 unknowns here, but it's up to defining up to scale. So this means that we'll only be able to define the third element as a linear combination of the first 2 elements here. And what happens here is that we'll only need 2 constraints to solve for this null space equation here. So we can stack these 2 together. That means that let's call this guy here A1 or AI here. So what happens here is that I can have 2 equations here, A1 and A2, and I can stack them together such that it becomes S11, S12, and S22 here equals to 0. So this would become a 2 by 3 metric, and this would become a 3 by 1 vector over here. Hence, this will be our familiar equation, the homogeneous linear equation of AX equals to 0 in linear algebra. So we can solve for the null space of X over here, or S over here, and that would be the equation, that would be the solution that we get for the S vector over here. And once we have solved for S over here, since S is equals to K transpose here, we can, this is a square root matrix. This means that this is a square matrix of K, and K would becomes the square root of S, and this is denoted, or this is given by simply the Cholesky decomposition. And so once we have obtained K, we will be able to get HA over here, which we can use to remove the affine distortion from the image completely, and we'll be left with the similarity distortion, which we will not be able to remove unless we know the corresponding points in the 3D scene. And so in the previous example, I've shown how to remove the remaining affine distortion after we have removed the projective distortion from the line at infinity. So this is actually a 2-step process that we use to rectify the image with projective and affine transformation to the original image. So this is actually a 2-step process to remove both the projective and the affine transformation from the image. So now let's look at one step process on to remove. So given an image with both projective and affine transformation, we are going to remove it completely. That means that recover the undistorted image from a one-step process here. And this can be achieved by identifying the C infinity star, the projection of the C infinity star directly on the perspective image, as compared to what we have seen earlier, that we have identified C infinity star, the projection onto the affine image. So in this case here, we'll directly make use of this equation that we have derived earlier. C star prime equals to this expression over here, which consists of both the projective and affine transformation inside here. And we saw earlier that these two matrices can be multiplied together to get this expression here. So now we are interested in finding K as well as V that represents the affine transformation as well as the projective transformation. And we can do this by identifying the orthogonal pair of lines L prime and M prime directly on the perspective image. So this means that the perspective image is containing the affine transformation as well as the projective transformation. We'll do the same thing. We'll simply, from this particular image here, we'll identify a pair of line which is supposed to be orthogonal in the real world. So in this case here, I'm going to call this L prime and M prime over here. And here I can express this, substitute it into the constraint equation, onto the orthogonal constraint equation that I have seen earlier. And this would give us this equation here. Each line here will give us one constraint over here. And we can rewrite this into, this is going to be a 1/6 matrix over here, and this guy over here is going to be a 6/1 vector, which consists of A, B, C, D, E, and F. Because we can see that from here, we can collectively call this into S, which is equals to S11, S12, and S21 that we have seen earlier. And V here would be another 3 more elements in the last row of HP, and this would be a 3/1 vector here. So there are 3 unknowns plus another 3 unknowns in S. Altogether, there are 6 unknowns in this equation here, which we can rewrite into this form here. So we will call C here as a vector of A, B, C, D, E, and F, which is represent the 6 unknown in our constraint equation earlier. And since this can be stacked together, each constraint gives us this equation here. We can observe more constraints. We have 6 unknowns here, where it's defined up to only a scale. And here, this means that we altogether we need 5 constraints to solve for this null space equation here. Let's call this guy here as Bi, for example. All I need to do would be to, each pair of lines is going to give me a constraint. I'll stack them all together to form this equation here, C and equals to 0. So this is this would become a 5/6 matrix, and this would become a 6/1 vector as usual. And then what happens here is that this becomes our famous null space, or the homogeneous linear equation AX equals to 0, which we can simply solve for C here by taking the SVD of this guy here. And so hence we will be able to, once we have solved for these 6 unknowns over here, we'll be able to decompose it and put it back into this equation here. Note that I have mentioned in example 1, the 2-step process. That means that I'm going to remove the projective distortion with L infinity first, and then remove the affine distortion using C infinity star. And this is also known as the stratified approach. And the 1-step process is to directly identify the projection of C infinity star on the perspective image and directly computing the unknowns of HP and HA together.